My name is Umut Aydemir from Koç University, I am actually the director of this Koç University Boron and Advanced Materials Application and Research Center. So today I will briefly describe you our center and then what kind of, let's say, like research activities are carried out in our center. Main focus will be on thermoelectrics. Okay, so this center is was founded in 2017 in collaboration with a company, and currently we have 28 researchers with 4 scientists, senior scientists, 2 postdocs, around 15 graduate students, 4 undergraduates, 2 technicians, and a visiting scholar. So our main research objectives are designing novel high-tech boron-based materials for advanced applications in the fields of energy, metallurgy, biomaterials, automotive and space industry, conducting groundbreaking interdisciplinary research in a broad spectrum of state-of-the-art materials, including thermoelectrics, superconductors, batteries, catalysts, hydrogen storage materials, laser crystals, and materials showing unusual properties like thermal contraction with heating. So we would like to patent materials with high potential of industrial applications, and we also initiate pilot scale production of these materials in collaboration with our industry partners. And last but not least, we establish a pioneer outreach program to develop an interest in boron and advanced materials research for whole Turkish community. Okay, now why boron? Maybe you are interested in why we are interested in or why we are doing research on boron-based materials. So let me tell you the motivation. So boron in industry is mainly used for glass fiber to make glass fiber, ceramics, borosilicate glass, in agriculture for fertilizers, and in drug and cosmetics. In more advanced applications, as you know, this is a magnesium diboride superconductor, which is superconducting around 40 K, which is actually relatively high TC. And then it is used in energy. You can make magnets with this magnesium diboride. Boron-10, an isotope of boron, is also a nuclear absorber, which can be used in nuclear power plants. Military use, boron carbide, for example, is a very mechanically stable material, and it is quite lightweight material. That is why it is used in armor. It can be used also in airbags. Now, the world boron production capacity for 2018 is around 4.1 million ton, and Turkey itself is providing almost like 2/3 of this boron production. Now look at the revenue. 2018, the total revenue is around $30 billion, which is quite big. But Turkey gets only 1 billion, which means we are producing 60% and getting only 3%. Now, our main motivation is to convert the boron from the mineral source to high-value materials. So, in this case, we are doing some energy-related research like superconductors, fuels and propellants, absorbers for nuclear reactions, or pyrotechnic materials. We do also make research on, for example, next-generation 2D materials. So we try to make borophene, which is the boron version of graphene. So which means instead of carbon, we have boron, and it shows like extremely interesting, let's say, like properties, even superseding the graphene. So we make also refractory materials, and we do some high-tech ceramics and etc. And we do collaboration with some other professors, and we are just like trying to produce biomaterials for cancer therapy. This is boron neutron capture therapy, or we try to produce therapeutic nanoparticles. And we do also prepare some composite materials or materials which can be used as missile fuels. Okay, besides boron-based materials, we do also other advanced materials for thermoelectrics. You can see this is a Curiosity rover, which is powered by these radioisotope thermoelectric generators. We do research on batteries, catalysts, for example. This boron-based magnesium diboride is also a very good catalyst. So in addition to these superconducting properties, it is also a very good catalyst which produce basically hydrogen as a clean energy source from water splitting. We work on superconductors, not only magnesium diboride, but even clatrates, for example. They show superconducting behavior. Some laser crystals we develop for niche applications, and we work on these materials displaying zero or negative thermal expansion. Most of the metallic materials expand as you heat them, but these materials, because of their unique crystal structure, they have either zero thermal expansion or contraction, negative thermal expansion. We do this with collaboration with other research partners. So just to show you our infrastructure, this is one of our lab with a laser flash apparatus here, ZEM3, resistivity measurement, thermal conductivity measurements, our XRD, thermal analysis with DSC, TG. We have glow box for air-sensitive materials. We have our own SPS to sinter powder materials, high temperature furnaces that we can heat up above 1500 C. Some other furnaces that we grow single crystals, for example, for vapor transport method. We do some battery research in this glow box as well. And here you can see that this is a cold isostatic press that we sinter the materials at low temperature, at room temperature, if we try to avoid high temperature annealing. So here are the companies that we are interacted with. So we do provide some service activities for, let's say, like governmental companies. They are mostly like national or like defense companies. So we also do collaborate with others or finance with other private companies. And we do collaborative research with some international and also the national universities here. Okay, so thermoelectrics, today there were a couple of talks given by experts. They were describing the thermoelectric effect, but let me revisit here one more time. So out of 100% energy, still mostly from non-renewable energy sources like petroleum, coal, natural gas, you can see that only 1/3 of this energy is provided for energy, like for the energy services, which is the useful part of this energy. 2/3 is rejected as mainly waste heat. So our main motivation is to convert this waste heat into electricity to kind of like contribute to our global energy sustainability. Okay, these materials are solid-state materials, which means everything is happening through the atomic scale. They don't have any moving parts. They don't need maintenance. They have long and scalable life, and they can be scalable, which means you can do micro scale application to like large-scale applications. So for a very long time, they have been used for powering the spacecrafts, for example, Voyager, which is investigating the interstellar space more than 45 years now, is powered by these multi-mission thermoelectric generators. So for the current ones, for example, Mars Curiosity rover, this rover, and even the last one, the Perseverance, for example, that was sent a couple of years ago to Mars, they are still producing their energy through this multi-mission thermoelectric generator. So they use the radioisotope decay, the heat produced by a radioisotope decay of plutonium oxide, and convert this heat into electricity. So you can also convert waste heat in automotives or like automobiles, for example, to kind of like power the lighting, for example, in the car. You can just like use it for energy harvesting, for example, as a medical sensor or smart watches, basically. And then, besides this power applications, they can be used for cooling and thermal management, which means you can create these small refrigerators which needs more precise cooling and noise-free precise cooling. And then you can just like use it for cooling the car seats. Optoelectrics actually, or detectors, they need more, let's say, precise local cooling. So thermoelectrics can provide solutions for that. So here are the thermoelectric theory. These are based on the Seebeck effect. So this is for power generation and Peltier effect for cooling. So here we have NNP type semiconductors. And then if we apply this circuit, we create such a circuit and apply thermal gradient, then this produces voltage, because we force these charge carriers to move from hot side to the cold side, similar to the gas materials, for example, and this creates a potential difference. So this potential difference that you create per temperature gradient is called the Seebeck coefficient. For the same circuit, instead of applying the temperature gradient, if you apply current, then you create yourself some temperature gradient, which means you can use it as a Peltier cooler. So this part will be cooled, this part will be heated. You can dissipate this heat with some methods. So in the materials part, we have this ZT called the thermoelectric figure of merit, dimensionless thermoelectric figure of merit, related to the Seebeck coefficient square times the electrical conductivity divided by the thermal conductivity times the temperature. So for high thermoelectric efficiency, we try to get good electronic properties, but at the same time lower the thermal conductivity, which is quite demanding and hard. So if we go to the efficiency, so this is related, device efficiency is related to the Carnot efficiency times the function of this material ZT. And you can see that rather than having high ZT at one particular temperature, we target the high ZT over large temperature window so that we have high average ZT, basically. Okay, so these are the thermoelectric couples. You can see we have some metal substrate here, some ceramic parts. So you create the modules when you just like put these thermoelectric couples electrically in series and thermally in parallel, and like tens of them. Okay, so what are the ideal thermoelectric materials? So phonon glass electron crystal is telling these materials. So this is telling that the materials should have very good electronic conductor like perfect crystals, but at the same time they should have low lattice thermal conductivity like glasses. So this is hard to make in one particular material because of this conflicting transport coefficients. Because if you have large carrier concentrations, okay, so this is provided in the metals basically. Metals, they have large carrier concentration, but when the metals have large carrier concentration, they have low Seebeck coefficient. So on the other hand, for the semiconductors, you can see that they generally have low carrier concentration and large effective mass. So here you can see that the power factor, which is the multiplication of this Seebeck coefficient times the square of the Seebeck coefficient times the electrical conductivity, is maximized for basically the carrier concentrations within this window. So let's say 10 to the 19 to 10 to the 21 per centimeter cube of carriers. And this is kind of like valid for the heavily doped semiconductors. So you should tune the carrier concentration in a sense to tune the electronic properties. So for the thermal part, thermal conductivity part, you can see that this is composed of two contributions. One is the lattice thermal conductivity, another one is the electronic thermal conductivity. So this is kind of like Wiedemann-Franz law. So the electronic portion of thermal conductivity depends also on the electronic structure of the material. Now the only thing which is actually independent of the electronic structure is the lattice thermal conductivity. So it means we have to find some materials that kind of display good electronic properties and low thermal conductivity, and you can tune these properties either by charge carrier optimization or lowering the lattice thermal conductivity. So let me describe how we can do that. So the first thing that we have to establish for the good electronic transport is the band gap. Now materials should have a band gap, because if you don't have a band gap, then you have both kind of like carriers, both type of carriers. So this band gap should be basically small enough so that you can dope this material either p-type, as you can see here, the Fermi level in the valence band, or n-type as the Fermi level in the conduction band. But it should be also large enough, as I said, so that you don't have two separate n and p-type carriers like electrons and holes at the same time, which kills the Seebeck coefficient basically. Now what about the thermal conductivity? So for thermal conductivity, I told you that this is the electronic part is connected to the electronic structure through Wiedemann-Franz law. So the lattice one, you can see here, the lattice thermal conductivity, it is kind of like dependent on the specific heat times the phonon velocity and the phonon mean free path. So you can lower this relaxation length or the phonon mean free path by introducing different scattering sources into the microstructure, by nanoparticles, by introducing large density of grain boundaries, and also some point effects. In an alternative way, you can go from, let's say here, this is the silicon, the lattice thermal conductivity of silicon with respect to the temperature, the natural silicon has still high thermal conductivity, but if you go lower the dimensionality, let's say like to 3D, to 2D or 1D, and then at the end, if you have, let's say, like the amorphous one, just like make nanoparticles with the amorphous nature, then you can basically lower this lattice thermal conductivity to the glass regime. So you can also, as I said, introduce some nanograins, which means, let's say this is your grain structure, you have this grain sizes, large grain size. For example, if you grind this, you can create smaller grain size, which means you introduce a lot of densities, grain boundary is here, you increase the grain boundary density, and this is scattering more of the heat-carrying phonons and it can lower the thermal conductivity. So you can also create nanocomposites. So, which means you can, for example, introduce intentionally some, let's say, secondary phases either within the grains or at the grain boundaries, and they also act like phonon scattering centers. So you can, this is nicely shown, for example, for nanoparticles of lead telluride inside the silver telluride, or by using the phase diagram of these systems, you can create such eutectic structures, and these are like lamella structures of lead telluride and antimony telluride. They have also kind of like impact on lowering the thermal conductivity. So for the lattice part, we can also tune the velocity because this lattice thermal conductivity depends on the phonon velocity as well. Here, this is, let's say, like simple scheme showing that if you have small unit cell composed of exactly the same atoms, you have only one phonon mode here, longitudinal phonon mode, and the slope of this dispersion curve is giving you the phonon velocity. Now, if you introduce a secondary atom, you just increase the size of this crystal structure, then this one mode falls into two. If you introduce more, you increase the lattice, and then you shrink the Brillouin zone, and then you can see that you create a lot of optical high-frequency phonons as opposed to low-energy acoustic phonons. And these phonons, you can see that they are flat, which means their phonon velocity is almost zero because the slope is zero. In this way, if you just increase the size, if you increase the number of atoms, different types of atoms, you basically have larger unit cells, which leads to more low-velocity optical modes that lowers substantially your thermal conductivity. This is nicely experimentally shown for a particular family of materials, which is called the Zintal phase. So you can see that this is lithium zinc antimonide, strontium zinc antimonide, all the way to ytterbium manganese antimonide. Similar materials, like the atoms are similar, but the difference is the complexity. You can see that this is only 6 atoms per unit cell, and you increase the unit cell size, you introduce different, let's say, like local environments. Here you can reach 208 atoms per unit cell. Large unit cell, very different local environment leads to lower thermal conductivity, experimentally shown. So this is this one, lithium zinc antimonide, and this is for the ytterbium manganese antimony. So this is extremely low lattice thermal conductivity. And you don't need to do anything. This family of material has complex unit cell which introduces or which shows already low thermal conductivity inherently. So now let me just tell you what is a Zintal phase. Maybe this is the first time you are hearing about it. So most traditional thermoelectric materials like lead telluride, silicon germanide, these are the materials used for this space applications. They are covalently bonded materials, you know, like lead telluride, silicon germanide, typical covalently bonded materials. And they are composed of these p-block elements. Zintal compounds contain both electropositive cations, as you can see here, these ones, that donate their valence electrons to the more electronegative, let's say these p-block elements, which use them to form the correct number of covalent bonds such that each element has a filled, shell, which means it is kind of electronic transfer from the cation to the anion. And this electronic transfer leads particular connectivity of the atoms. So, and I mean, this cation can be, again, these alkali metals, alkaline earth metals, rare earths, even transition metals, and generally the anionic part is the p block element. Now, these zintal phases, they are unique because they have an anionic substructure. You can see here different anionic substructures, 0-dimensional, 1-dimensional, 2-dimensional, layered-like, or even 3-dimensional structures. They have strong directional 2-electron, 2-center covalent bonds, which accommodate in the cavities, as you can see, these blue atoms, the cations. These cations act like soft, non-directional. They have soft, non-directional ionic bonds with the covalent framework. So they are kind of like composite materials in atomic scale. So most of these materials inherently show p-type properties. So 122, 526, 313, 14111, 122, they inherently show p-type behavior because of these cation vacancies. Generally, when you make them, you observe that there is a very stable defect in the structure, which is a cationic defect. Okay? Calcium, magnesium, or whatever. They show inherently p-type behavior. But only recently, there was a paper coming out from the Panasonic group. They just showed that this material, magnesium 3 antimony 2, which is a typical zintal phase with some magnesium deficiency, it was showing p-type behavior so far. It can be made n-type, and the n-type analog can show even better thermoelectric efficiency. So they showed that you can make this n-type, and you can see that the ZT is generally 1 for state-of-the-art materials, but this easily reaches to 1.5 at relatively high temperatures. To make this n-type, there is a unique strategy. You have to add excess magnesium. When you start making this material, you have to add some excess magnesium to suppress the formation of this magnesium defects, which leads to this p-type character. So we knew that you can make this material n-type, but then we just thought, how can we improve the thermoelectric efficiency, or what else we can do? So we applied a melt centrifugation method, what we call melt centrifugation method to this material. We used this melt centrifugation technique on bismuth antimony telluride, which is the best low temperature material actually. So the idea is this: you add intentionally an element, for example tellurium, inside this material, bismuth antimony telluride plus some excess tellurium, and with a technique you just remove this molten tellurium at high temperature. So this could be done with spark plasma sintering. What we did is this: we just put a little bit of tellurium, excess tellurium inside. We just put this material in an oven, high temperature, and then we quickly took away it from the oven and made the mass centrifugation and removed the tellurium from this phase. And we saw that in bismuth antimony telluride, you can have a lot of grain boundaries, ordered grain boundaries, and within the grains, we have a lot of lattice dislocations. You can see that in like lattice dislocation networks or like regular lattice dislocations. And this lowered the thermal conductivity substantially. This is the non-centrifuged material, and you can see that you can lower it to 50% thermal conductivity, and ZT can be also improved a lot. Okay, idea was this: as I said, you have bismuth antimony telluride. If you add tellurium, you have this eutectic point here. If you just heat this material around 500 degrees, you can remove this melt, and you can create such microstructural features. So we thought, okay, why not applying this to magnesium antimonite? Why? Because the nature is similar. Here you can see this is magnesium 3 antimony 2. Here we have magnesium, and between magnesium and magnesium 3 antimony 2, we see also such a eutectic temperature here. So we just went a little bit higher than 650, maybe 750, by adding excess magnesium and applied this technique. So we added 20 and 46 weight % excess magnesium, and then did some research to see the effect of it. So this is done in situ and external addition. Let me explain it to you here. So you can put all these materials in a steel vial, do high energy ball milling, let's say 2 hours of high energy ball milling. If you add the magnesium at the very beginning, this is in situ. If you add magnesium after you do this 2 hours ball milling, if you add the external magnesium afterwards, this is called the ex situ preparation. So this will lead to powder material. You do sintering with spark plasma sintering at such certain condition to make this bulk material. And then we seal this bulk material in a quartz ampule under protective atmosphere, because if you take this, put it in an oven, it will be oxidized. To avoid that, we just put it in a quartz tube and then put this in an oven. Did a quick centrifugation. You can see that the magnesium at the molten state, it just comes out from the bulk piece, and you can clean this and see that, investigate the microstructure. Of course, the first thing we do is XRD for phase analysis, TEM, SEM for the microstructure analysis, LFA for thermal conductivity, and ZEM3 for the electronic transport characterization. So this is the XRD diagram. This is the theoretical pattern. You can see that this is magnesium 3 antimony 2 as it is. Then we add a little bit of bismuth and tellurium to basically tune the electronic properties, and then add extra magnesium. By adding extra magnesium, you can see that sometimes even we introduce this melt centrifugation, there is some residual magnesium left in the structure, microstructure. You cannot 100% remove it with this one, but we could also remove it 100%. So it depends on the experimental conditions. So this is the microstructure with TEM without melt centrifugation. You can see that very condensed, highly condensed, regular microstructure, let's say. And you can see that this is the average grain size, couple of 100 nanometer. What happens if we apply this melt centrifugation? We create large pores, as you can see here, but at the same time, small pores, which means microscale pores or like nanoscale pores. At the same time, you can see that we create these ordered grain boundaries. They are nicely ordered, right? It is completely different than these grain boundaries. Plus, we show that we have also some lattice dislocations within these grains. And we hope that this substantially reduces the thermal conductivity. So here is the electronic transport characteristics. This is magnesium antimonite. Resistivity is quite high, as you can see. If we dope it with bismuth and antimony, bismuth and tellurium, we can just like lower it to here, the resistivity. And then with this melt centrifugation technique, we can also tune the electronic properties together with the Seebeck coefficient. You can see that we have high, like low Seebeck coefficient with high carrier concentration, or high Seebeck coefficient with low carrier concentration. So the thing is this. You see that the power factor is still high for this MSBT phase, in which we don't apply any melt centrifugation. Okay? So we just checked the weighted mobility here. You can see that this material is around, let's say, like 70–75% dense, which means there are 25% kind of like voids or vacancy, but still the weighted mobility is not much lower than the other bulk materials, in which the density is around 98–99%. It is quite good, which means electronic transport is not severely affected by these methods, although the power factor is slightly low. So power factor is slightly low, but you can see that the thermal conductivity is substantially low. This is undoped. This is doped material around 1.2. When we do melt centrifugation, the total thermal conductivity is 50% reduced. And lattice thermal conductivity as well. So this overall leads to around 43% enhancement if you just compare it with the MSBT phase. You can see it here. And if you calculate the device ZT, we can see that we can reach around 1 at this temperature, and the theoretical efficiency of this device would lead to around 12%. So these are not experimental, but theoretically calculated efficiencies. Okay, so far it was for magnesium antimonite. We did some research also for the bismuth antimony telluride and bismuth selenide telluride. These are the low temperature materials that are mainly used for Peltier coolers. So you can see that this is the P-type, this is for the N-type materials. For the low temperature, they are kind of like the best materials. So bismuth antimony telluride, BST phase is very good for the P-type, and bismuth selenide telluride is very good for the N-type. So the others cannot compete except for the magnesium antimonite so far. So here are the unique crystal structure of this. So we see in this crystal structure these layers of bismuth tellurides, which is called quintuple layers. So here in the microstructure, you can see that in the crystal structure, we have these bismuth atoms octahedrally coordinated with the selenium, with the tellurium. And you can see that if you just like do kind of like solid solution of bismuth telluride with the antimony telluride, you can also engineer the mobility, effective mass, and the band gap. And we just like focused on these two materials. One is with bismuth 0.3 and the other one is bismuth 0.5. For the selenium case, you can do the same. You can just like basically do solid solution of bismuth telluride with the bismuth selenide. They have the same crystal structure, which means you can combine them in any ratio you want, and you can also optimize their transport properties. So now we saw that in literature, copper is a very good dopant to basically optimize the thermoelectric properties of bismuth telluride. And while we saw this paper, we were basically making another research on copper telluride. So this copper telluride is a synthetic ricardite mineral. It shows nice properties. Like here, you can see that you can just straightforwardly make it with solid state synthesis. You see that this is very good crystalline, purple-like crystalline material. So you can make it with this method. And the crystal structure is also kind of layered-like. It doesn't show here, but it is like layered-like structure. So here you can see that we have very nice grain distribution. So this is the polarized optical image, optical light image. So you can see that very nice grains oriented in different ways. It is like an art. And the good thing with this material is this. At low temperature, this material is undergoing a phase transition at around 150 C. And at little higher temperature, around 350 C, it undergoes another phase transition. And this phase transition nature is reversible, which means you heat it, you see these phase transitions, you cool it, you see the same phase transitions at around the same temperature. And at low temperature, this shows a metallic character, which means here the ZT is almost negligible. And after this transition, you can see that suddenly the ZT goes up quite a bit. Still low, around 0.2, but it is promising. Now, as a copper source actually, or metallic nature, we just put this material in bismuth antimony telluride. So here we prepared the bismuth antimony telluride, solid state synthesis, grind it, put it here in a vial, steel vial, added copper telluride, did XRD analysis, SPS, LFA, and all the other analysis, transport characteristics. And these are the X-ray diagram. So here, this is the theoretical pattern for copper. This is copper telluride. This is the bismuth antimony telluride. Here, you can see different, the black ones are the bismuth antimony telluride. The red one is copper telluride. So almost single-phase bismuth antimony telluride, no detectable copper telluride. So these are the copper telluride because the amounts of doping here, you can see it is quite slow. This is X from 0 all the way up to 0.15. Small amount of doping. Similarly, this is the BST5, which is bismuth 0.5. This is BST 3-phase, which is BST 3-phase. Okay, here are the microstructure. You can see nicely that these are the grain boundaries, very good oriented, I mean like not oriented, but let's say like well-resolved grain boundaries. And at the grain boundaries, we see mostly copper telluride. Copper telluride that we introduced there are mostly decorating the grain boundaries. So this is good because this is a metallic material, might help with the electronic conductivity, but at the same time, it is a secondary phase, can lower the thermal conductivity. So here you can see this is the mapping, elemental mapping. This part, so this is this region. You can see that this part is bismuth antimony telluride, and here this black one means this is antimony deficient, but copper excess. So which means this is copper telluride, and this is bismuth antimony telluride. This is the same. You can see that this is copper telluride, and the rest is bismuth antimony telluride. So this is the optical images. This is the cross-plane direction, these two, and this is in-plane direction. There is a kind of like striking difference between them. You can see that in the in-plane direction, we just see this very nice layers of bismuth antimony telluride, which means main orientation is towards the in-plane direction. This is the perpendicular to the SPS direction. This is also nice because this can also improve the electronic transport through in-plane direction. So here are the transport characteristics. You can see that this is undoped material, low electrical conductivity. If you dope it with copper telluride, you can see that you can really tune with the copper telluride amount, the electronic conductivity goes up all the way. And Seebeck coefficient, in similar manner, you can see that they are high because carrier concentration is probably low here. And as you increase the copper telluride amount, carrier concentration probably through copper doping, for example, of this material is getting higher and Seebeck coefficient gets lower. Thermal conductivity, of course, is a metallic material, which means metallicity actually increases the thermal conductivity as well. Okay? Let's see the overall effect. So this is kind of like no heat, nothing like our typical BSC. This red one is that we made 10 minutes of ball milling, and the others is 10-minute ball milling plus the copper telluride addition. So still, at low temperature, you can see that this is comparable, like our best material is comparable at low temperature with the 10-minute ball milled material, but at slightly high temperature, like 450 K, it outperforms. Like we reach a ZT around 1.3. It is quite important improvement for this material. So this was cross-plane direction. We see similar effect in the in-plane direction. The transitions are like the same, almost higher electrical conductivity, lower Seebeck, little bit higher thermal conductivity, but still, especially, so this is 1.2 around when 10-minute ball milling is applied, and at higher temperatures, still, copper telluride addition of, let's say, 0.025 gives much higher ZT values, which means by introducing this nanoscale secondary phases, you can optimize the thermoelectric efficiencies or performance of these materials. So in addition to the transport characteristics, it is better to also check the micro hardness, or let's say like the mechanical properties of these materials, because when you do module applications, we want to have durable materials. Here you can see that this is a synthesized materials. They are black. This is bismuth 0.5. This is bismuth 0.3. When we add copper telluride in cross-plane or in in-plane direction for both of the cases, we see substantial increase in the micro hardness, the mechanical properties of this material. Okay, so here I need to acknowledge these funding sources, let's say, including TÜBİTAK. So this is our kind of like Kuban researchers, including my daughter, Lisa, my catalyst, 2-year-old girl. Hopefully she will join me this evening. So with her contribution, I could finalize this work. And I would like to thank you for your attention.
Thank you.
Yep.
Any questions?
Umut, thank you very much. I feel like I have been refreshed about the thermoelectric field because of your great presentation.
Thank you.
So I have just a couple questions about your zintal phase materials.
Sure.
Zintalate. So you said that magnesium looks like play an important role in the transfer properties of these materials.
Mm-hmm.
So have you ever tried like a calcium or sodium instead of the magnesium? What's the magnesium is preferred?
Okay, so you can tune the properties by adding sodium or other elements, because magnesium is, let's say, like 2 plus here in magnesium 3 antimony 2. If you add sodium, it means you are replacing 2 plus with 1 plus. So you are pushing it to the p-type material. So our motivation here is not to touch p-type, because we know that p-type ZT is much lower than the n-type ZT. That's why we were kind of like focusing on magnesium, not adding any alkali metals. But you are right, so instead of magnesium, you can dope it with calcium, 2 plus. Maybe you can lower the thermal conductivity even further. We didn't do it, but this is doable. It's a meaningful strategy. The only thing is this: maybe you will end up with calcium antimonide as opposed to like magnesium calcium antimonide. Because magnesium antimonide, calcium antimonide, separately, they are very stable phases.
Thank you.
Yep.
So maybe the last question I can ask you, the copper 3 tellurides is the same crystal structure of the antimony telluride, right?
No, they are completely different.
It's completely-
Copper 3 telluride has, I think, orthorhombic structure at the low temperature, and it goes to a tetragonal structure, and then to hexagonal structure. Like copper 3 tellurium 2 has different structure with the antimony telluride.
Okay, then your motivation for this study was like just to put some different nanophases in the structure, or do you have some idea to?
Yeah, exactly. So
Okay.
let me just show you here. Maybe I just like didn't mention it
And
quite
also
well.
maybe did you try for the N-type too?
Yeah, so the idea was this. So when we were dealing with this research, we just like found that there are a couple of research publications, let's say, they are dealing with this bismuth telluride with doping copper, which means they are doping this material with copper and getting better efficiencies. Now, okay, we don't want to repeat that, but we have copper telluride, which can act like a copper source, and at the same time, this shows this phase transition, strange phase transition, and it is metallic. We thought like, okay, rather than using pure copper, why don't we use copper telluride? Why? Because copper is a mobile ion in copper telluride as well. It has high ionic mobility. It can diffuse easily to bismuth antimony telluride, perfectly fine. And we have also tellurium. That's good because the main material has also tellurium, which means if there is any loss of tellurium, this can compensate this loss as well. So this was kind of like two different aspects that we introduced into the structure, and then saw that this is really working quite nice. So we didn't publish this paper yet. We are just writing it.
It's a very good idea.
Right, right.
So about the N-type bismuth telluride, did you like put some?
Yeah, I didn't show it here. Yes, we tried some bismuth selenide telluride, and then rather than copper telluride, we just dope it with boron actually. Carbon-coated boron or boron, and we could increase the ZT quite a bit. We did it as well. So around 20–30% increase, right.
Because the biggest problem for bismuth antimony telluride is the
N-type, exactly. We did it as well, but here I just showed these two results because this paper is also not written yet.
Yes. And also that's interesting that the mechanical properties also improve with this.
Right, exactly, exactly.
For
When you add,
model design.
I mean, this is the usual thing. Generally, this bismuth antimony telluride, as you know, very anisotropic material. There are some cleavage planes. It easily like breaks down the material. When you add this metallic, ductile material, it improves the mechanical properties. Meaningful.
Thank you.
Yeah.
Any other questions?
Yep. Here. Sorry. Bir tane daha sor. Maybe if you just say.
No. Okay, so you had a figure where you showed that with 0% copper telluride, the temperature trend was down in this
Let me
figure
show.
of merit. It's a bit later, I think.
Here
yes,
you mean?
Yes, yes. Now I have a very simple question. Both figure of merit and Seebeck coefficient have exactly the opposite temperature trend at 0% copper telluride and not 0%. Okay.
This one you mean?
Yes, yes.
The-
yes.
the red
this
one.
sticks out.
Right, like
So
this.
have
Yeah.
you some kind of simple, quick way to understand that?
Yes, sure. You mean Seebeck coefficient, right? This going down
Yes,
of the
yes,
Seebeck coefficient
yes.
as opposed to others.
Yes, yes.
Kind of, yeah. So that is the thing. Now, you can see that this is bismuth antimony telluride. Again, no copper telluride addition. This is called as-synthesized. The main difference between the black and the red is this. In the red, you may remember that I am telling you that this copper telluride is added by 10-minute ball milling after we synthesize this material. Now, we synthesize this material, did 10-minute ball milling without any copper telluride addition. Then the other copper tellurides also are done in the same way, 10-minute ball milling with 10-minute ball milling. So we wanted to show what is changing here, right? So the main thing is this: bismuth antimony telluride has very small band gap. You know, if we do ball milling in this material, probably we are also changing the composition and the electronic structure, which means probably we are shrinking the band gap. And if we shrink the band gap, as you know, if you increase the temperature, at one point, the minority carriers, let's say this is p-type material, the electrons will jump from valence band to conduction band, which means this will basically kill the Seebeck coefficient. So what is going on here is purely minority carrier effect, actually. We are activating the electrons as opposed to holes because of the shrinkage of the band gap due to purely ball milling. Because this ball milling, in the ball milling, we are kind of like forcing the steel balls to hit each other, and then we have powder material here, and this is creating local heating and local pressure, and this is probably introducing a lot of additional defect to the crystal structure and kind of manipulating the band structure. Yep.
Thank you.
Okay, thank you very much.